To get the capture or the Cadence software, first install it and then go to the location. Normally it is uh, stored in the installed in the C drive, so then you can get it from the start menu itself, but in my case I've downloaded it in the D drive, so I'll go to D, then I'll take Cadence SPB 17.2 tools, bin, then this is the icon, so it is opening. So these are my old files. So first when you do it, you won't have any files here. You can go to file, new project, then type something, whatever is the name of the experiment. Suppose I'm going to do differentiator. Then PSpice analog or mixed A to D, that is by default. This is the location where it is being saved. You can browse and find another location if you want. Okay, create blank project. Okay, then either press P or go to this place which shows place part. Then these are your libraries. Now in my case everything is selected. In this case only SEM400, that library is selected. If you want to select all, you can just do Control A. If you're doing it for the first time, just after installation, you have to add the libraries. So you can go here, click, you have all the libraries here, click somewhere, Control A, so that all the libraries are selected, then open, so that all the libraries will come over here. In my case everything is selected, so and select all so that you can easily get all the components. So now I'm going to do the differentiator circuit. So for that you need the resistor and the capacitor. So resistor and capacitor belongs to the analog library. There are other resistor capacitors also, but some may not work. So take it from the analog library itself. So just type R. So R bar analog. Analog is the library, R is the part name. Just go there, double click and drag the mouse so that you get the resistor. You'll get multiple resistors. If you want more than one resistor for any circuit, just click as many resistors as you want. In this case you need only one, so I'm just click right click and end mode, or just give escape. Now in the case of differentiator, I want this to be in the vertical position, so you can just press R so that it rotates, or alternatively you can go to edit and here you have the rotate option. So if you don't remember the shortcut key, you can just go there and rotate it. Now go to C, which is the capacitor, again belonging to the analog library. Double click, drag, escape, so you have the resistor and the capacitor. Now you need the source. Suppose I'm taking the sine wave first, so V sine is the sine wave. So the library is source, double click, drag, place it, then escape. Then you need the ground. So ground you can get it from the right panel, so just click it. So capsim is the library and 0 is the part name, so just double click and place it where you want and escape. Next you want to connect all the components with a wire. So you can go here and click and get the wire, or you can just press W, which is the shortcut key for wire. Then you click at one end of the any component and go and click at the other end of the other component. Click it there, otherwise the capacitor will get shorted. Then go and click again at the other end and to the other end of the resistor. Now from this end of the source to the resistor, then from the ground to the wire. Now if you don't want the wire anymore, you can just escape it so that the wire will go and you'll get the cursor back. Now we'll have to give the values for all the components. So N is nano, K is kilo. So I'll change the capacitor value to, I've already designed the differentiator for t equal to 1 millisecond. So capacitor value is 0.01 micro. Micro is U. No need to write farad. If you write also, it's okay. If you don't write also, it doesn't make much of a difference. I'm giving 160 ohm. You needn't stick on to the standard values here. You can go for the design values itself, since it's a software. If you give 150 also, it's okay. So 160 ohm. Then the sine wave. So sine wave, I want a sine wave with a peak amplitude of 5 volt. So peak to peak voltage of 10 volt. So V off is the starting value. Suppose that is 0 for me. I'm starting the sine wave from 0 to 5, 1 peak. Frequency T is 1 millisecond in the question. So frequency will be 1 by T, that is 1 kilohertz. AC value you give or not give, it's okay. If you are giving, just give 0. So I've given all the values. Now I have to go for the settings of the graph. So for that, go to PSpice. So the first time you do a project, you'll be seeing it as new simulation profile. After you set the new simulation profile, next time onwards you'll be seeing it as edit simulation profile. So new simulation profile, just give a name for the graph. So I'm giving it as, sorry, diff some value, some name. Then another window will open. So this is suppose you have the graph. So what is the starting value? So we are going to plot the input and the output graph. So the x-axis is time. So I select time domain or the transient response. So that is by default. If you want some other analysis, you can go for that analysis. In my case, I'm going for the default one, time domain, that is the x-axis is time. So run to time is the, if you have the graph which is the last value, start saving data after is the first value. So better don't start with 0. You can start at an intermediate position. So here suppose I'm giving it as 800 milli. Why milli? Because I've selected 1 kilohertz. So everything should be in milli. To say, suppose my one cycle is 1 millisecond. So I'm going for 5 cycles. So suppose 805 millisecond, and step size can be anything small. 0.1 milli, it can even be in micro. Then okay. Then you can go for the marker, place it at the input. So we'll first check the input. So escape the other marker. We'll first observe the input. So this is C1 and this is one of the nodes of C1. So now you run. Okay, so we had an error at first, so that is due to the missing value in AC. So in some versions, if you don't give AC value also it works, but I guess in this you have to give an AC value. So I've just given it as AC equal to 0, and then I'm running. Here you've got the input graph. So let's see, we have given the input to range from 800 milli to 805 milli. 800 milli to 805 milli. So if you see the graph, it is from 800 millisecond to 805 millisecond, and the input is given as with a frequency of 1 kilohertz and amplitude of 5 volt. So amplitude is 5 volt and frequency 1 kilohertz means time period is 1 millisecond. So 800 to this is 80. So we'll, here it is 800 to 801. So one full cycle is 1 millisecond. Okay, one positive half cycle and negative half cycle together it is 1 millisecond, just as we gave it. Now I'll place another probe at the output. So when I kept the probe, you can see a red color here. So we know that output is much less than input, and output is much less than input. So that is why it is a very tiny waveform. So in order to see that in a better way, in order to measure the value, amplitude, etc. So what I'll do is I'll go to plot and add plot to window. So I'll plot the output here and the input will remain here. So the red probe is VR12. So we'll place the VR12 here. So how do I do it? You go to trace, add trace, and I'll check the VR12 from here. I'll select it from here. Okay. So that VR12 comes here. Okay, the color is different because when you're using two graphs in the same plot, it'll be of different colors. When it is different plots, then it came as the same color. So I'll just remove the VR12 from the previous graph. Just click it, select it, and press the delete button in your keyboard. So this is your differentiator. Input when it is at 0, output is at positive peak. When input is at positive peak, output is at 0. And when input is at 0, output is at negative peak, and so on. Okay, and you can see that the input wave is very small since it's in another scale and not as the same scale as the input. That's why you're seeing it almost in the same size. So actually it is less than 100 millivolt. So 1, 2, 3, 4, 5. 5 divisions equal to 100 millivolt. So 1 division is 20 millivolt. So 20, 40, it's about 50 millivolt. Okay, so the peak value is approximately 50 millivolt, and this is minus 50 millivolt. So that is how you plot the input output waveform for a differentiator. Similarly, you can do it for integrator also. Uh, so next what I'll do is I'll just change the sine wave to a square wave. So I'll just remove the sine wave form at the input, and I'll get the part. So from the place part, that window, I'll check for V pulse. V pulse. So that's also in source library. So I'll place it over here. Escape it. So now here you have multiple things. So V1 is the initial voltage, V2 is the final voltage. So that is, in the case of a pulse waveform, it is the positive peak and the negative peak. You can give it in however you want. That is, V1 can be positive peak or V1 can be negative peak. So just if I'm giving V1 as say +5, then V2 I'll give as minus, sorry. So these are placed very close to each other. So what I'll do is I'll just select it and drag it so that I can select the next one. So V2 is -5 volt. So I'll just place it a little away. TD is the delay time. So for a square wave, the delay time can be 0, but in some of the versions 0 does not work. So I normally say that keep it very low. So I'm giving as 1 nano, a very low value. Then the rise time, that also 1 nano. Ideally it can be 0, but then it doesn't work at times, so I'll just keep it at a very low value. So rise time, delay time, rise time, fall time, TD, TR, TF, all I've kept it at 1 nano. You can keep it at some small value. Then you have the pulse width and the period. So again, we have designed for t equal to 1 millisecond. So t 1 millisecond means period is 1 millisecond. So period is 1 millisecond, 1m. So pulse width is the width of the pulse. That is, if you want a square wave whose pulse width, that is a period is 1 millisecond, you can keep the pulse width as half the period. Okay, so that is 50% duty cycle, that is on time equal to off time. The time where the square wave has its positive off cycle, that time is equal to the time where it is in the negative off cycle. So pulse width, I'm keeping it as half of 1 millisecond, that is 0.5 millisecond. Okay, so now we'll just check the output, input and the output. So I have not changed anything else. I've just kept the source as a different value. So here, if you can see, I'll just plot it in a different scale so that you can see it better. So VR12 is our output. So hope you can view it. So this is my square wave and this is my spike. So spike is sudden change in voltage, and spike value will be greater than the input wave. So I'll just make it a little more darker so that you can see it properly. So this is my spike, and I'll just, that is, you click on the trace, right click, select the trace, click on the trace so that it gets selected, right click, then go to trace property, then you can change the color if you want, and if you want to if it's not very visible, you can just change the width, increase the width so that you can see it properly. So when it is negative half cycle, you have a negative spike. Positive half cycle, you have the positive spike. And uh, as per theory, whatever is my input voltage, you get the double the value for output if it is within the correct design limits. That is, I designed for t equal to 1 millisecond and I've kept the frequency as 1 kilohertz. So that is the range of frequency that comes within the range of frequency wherein it will differentiate differentiate properly. So in that case, you'll get the almost the double the value as the output. So this is the only case where you get V naught greater than Vi. In all the other input cases, you'll get V naught less than Vi. Okay, so that is it. And now I'll just change the delay by changing the delay time, rise time, fall time, and the pulse width. You can change a square into triangle. So suppose, let's see, I make pulse width equal to 0, and let's see what happens. I'll just change the output. So now it's still a square. I'll increase the value of TD, TR and TF. So TD, let it be like that. Rise time, fall time, I'll make it as 0.5 milli, and fall time as again 0.5 milli, and run it. So I get a triangle. So the same V pulse is used. What I did is rise time. It is taking some time to rise. So that I made it as half the time period, and fall time again half the time period. You can keep it however you want the square triangle to be. You can change the rise time and fall time. Just remember to make pulse width equal to 0. Okay, so from here 800, say 800 to 801. So this is one time period. So I have the triangle wave here, and I'll place the, so even without placing the probe, you can just go to plot, add plot to window. Since the output will be small, I know that, so we'll just go to the VR12 and OK. So what we get here is, for triangle, the differential is square. There is a slight distortion here. Otherwise, it is correct only. So rising edge of the triangular, exponentially rising edge of the triangular waveform, my output is square positive half cycle, and falling edge of the triangular waveform, I have the negative edge. Okay, so that is how you do the sine square and triangle for a differentiator. You can do similarly for the integrator, just reverse the R and C and design properly and put the values. So that is transient analysis basics.